So these are actually the transformation what we know. So y prime is equal to y, z prime is equal to z, and t prime is equal to t. So this absoluteness of time we have in Newtonian relativity and the Galilean relativity. So these are the Galilean transformations. If we see implications of these kind of transformations, so we are having this very equation, an important equation in Newtonian mechanics, d2x by dt2. Okay, so this is the force law, and in Newtonian mechanics we derive all the conservation laws, any physical quantities we derive from where? From this very equation, is it? Now if we look at this, so this is fundamental equation to Newtonian mechanics, is it? So all the mechanics you can derive from this very equation. If we look at this kind of equation, okay, so this equation is invariant under this kind of transformation. You just differentiate this this very equation. What you will get after differentiating? So you will get some u prime is equal to u minus v, is it? So v is the relative velocity between the frames, and u prime is the velocity what you measure, okay, of another object which is moving related to that. So you are having two objects moving with respect to each other with the velocity v, and this is the relative velocity, or it is what we call the classical velocity addition rule. Okay. Now if you differentiate it again, because this v is constant, you just differentiate it, so you will get actually the acceleration. So that is same here, okay? Because mass is an absolute quantity in Newtonian relativity, you just multiply now mass, you will get what? Force same in primed frame as unprimed frame, okay? So that means this very equation is invariant under Galilean transformations, okay? So it means all the laws of the physics which are based on Newton, are all the quantities, are all the conservation laws which would derive from the Newtonian, are this very force equation, they are invariant under Galilean transformation, okay? So it fits with the definition. You are having all physical laws are invariant under Galilean transformation. The first principle, I mean the relativity principle, is it? So it fits with that kind of definition. But now let's look, let's apply this kind of notion to the velocity of light. Okay, let's apply this or these kind of transformation to the Maxwell's equations. Okay, Maxwell's equations we can sum up it in, okay, Maxwell's equation gives you the velocity of light, is it?
Yes, sir.
As a wave equation. Okay, so there is a factor. So if you are having a wave equation, let's say nebula square some psi is equal to 1 by c square partial 2 psi by partial t2. Okay, I should put as E. Okay, so as the electric field and same as for the magnetic field. Okay, so you can come with this. Okay, you can derive this very equation from the Maxwell's equations, and it gives you some constant, what we call the velocity of light. Now if you see if you let's try to measure the velocity of light in two frames of reference with respect to, okay, you are having one body that is emitting photon and you observe it from the another body. Okay, that body is moving with some, let's say, the velocity v with respect to the previous body. That means you should get a different value of velocity, is it? The experiments have been done, people have invented the concepts of the ether and so on, okay, and try to figure out what is the amount of shift in the light, okay, but all the experiments gave us the null results, okay, so we could not find any kind of that preferred frame, what we call it the ether and so on. So this is all the historical debate now, or the historical subject. The point here is, are these transformations really the true transformation between the coordinates? Okay, or if they are correct transformations, then the first question arises, few laws are invariant and few are not. So it's not a universal concept to have an invariant laws, okay, or the laws of physics are not invariant under all kinds of transformation, or under this kind of transformation, is it? Only the particular set of laws are invariant and another law are not invariant, okay? So much more. And second point, we could think Maxwell's, okay, for the Maxwell's equations, you need actually some different kind of law, or you need some generalized coordinate transformation under which both Newton's laws or all the laws of physics, whether they are the Maxwell's equation or any other laws, they should be invariant. Okay? So it is actually the second possibility what we need to look, because we cannot modify Maxwell's equations. Maxwell's equations are the absolute, they are the true equations representing the electromagnetic phenomena. Okay, so we need to actually modify these kind of equations. And it was actually many people worked along these lines, like say, I should say Poincaré, Lorentz, okay, Abraham Lorentz. There were many other people who tried to, convince for these kind of transformation, okay, but they were not able to postulate it boldly like Einstein did. Suppose Lorentz figured out these transformation rules, that space and time, they get mixed up, okay, but he was still reluctant in discarding the ether theory, okay. So it was ultimately actually Einstein who postulated a new theory, a generalized kind of kinematical theory, okay. So what we call it special theory of relativity, for which the Newton's laws of motion are actually an approximation. So there is usually people confused with many things. So in the microscopic domain, you are having the generalization of Newton's theory as the Schrodinger equation, is it? So you are having a quantum mechanics in the microscopic domain. But when you are having at the higher speeds, you take it as a special relativity, is it? So Newtonian mechanics or Newtonian laws goes to the special theory of relativity. But usually you are having a general theory of relativity. General theory of relativity of special theory of relativity. It's actually the generalization of Newton's law of gravity. Okay, Newton's force equation, you can think this F is equal to m relativistic behavior as the special theory of relativity. Okay, this kind of mechanics. But the gravitational rule, F is equal to g mm by r square, that is generalized to where? Theory of relativity. And general theory of relativity is not the generalization of what? Special theory of relativity. These are two distinct subjects, okay? General theory of relativity is a kind of what we say field theory, and special theory of relativity just it gives us the kinematics at the high speeds, okay, or the dynamical behavior, both kinematical as well as the dynamical velocities. So this, okay, now let's go to the postulates. Any question till now? So these things you already know. I just revise it a little bit. So you are having these postulates of what Einstein did. Okay. So the first is the same thing, Galilean relativity principle. Let me write. Okay. Let me go slowly. This is known as principle of relativity, the first postulate. This is a very important principle. It can be generalized. Okay, so this is very foundational principle, this principle of relativity. So it says all laws of nature are identical in all inertial frame. Okay, what does that mean? The equations expressing the laws of nature are invariant with respect to transformations of coordinates and time. one inertial frame. Okay, so this is the first postulate of theory of relativity. You are having all the laws invariant and okay, in all inertial frames of references. Okay, so if you make a coordinate transformation, what we see, okay, the coordinate transform what we are trying to derive now, okay, usually we call them as the Lorentz transformations. So under those transformations, you will be having all the equations of motion, then invariant, or the form of the equations remains same if you go from one frame to the another frame. Okay, and the second postulate is what we call the universal velocity. Has everybody studied this relativity at some point of time? At least? Okay, those who have not come across, there is a book, very nice book by Robert Resnick, Special Theory of Relativity. Okay, Robert Resnick has so that is just a 100-page book. Huh? So just keep it at okay, keep it and read it in your leisure time. That's a very nice book. So you are having the velocity of propagation. Of interactions. So this is a very important thing. So propagation of interactions, okay, is the same. In all inertial. Okay, so you are having this the interactions between different bodies. Let's say you are having electromagnetic interaction. How it occurs? So it is through some electric and magnetic fields between the two bodies, and there is a proper mechanism how electromagnetic objects interact with each other, is it? Yes. So this kind of interaction, fundamental interactions, okay, so they occur at the speed of light, okay, and this speed is invariant. If you go from one frame to the another frame, you will see always bodies interacted via this kind of velocity, okay. So this velocity we call it the velocity of light, okay. So C, okay. Got it? Okay. Now let's take all the four fundamental interactions. I will tell you there is a subtlety in this kind of postulate. So take all the fundamental interactions. Let's say you are having, for example, electromagnetic interaction or the gravitational interaction. Okay, the different bodies interact. Okay, at certain. It is not something action at a distance. What existed in Newtonian relativity or Newtonian physics. So action at a distance means, suppose a body, when it tries to interact with another body, it acts instantaneously. Okay, or the interaction between them, or the interaction between any two bodies is instantaneous. So it means the velocity of the propagation of this interaction is infinite. Once the velocity is infinite, so everything will be instantaneous. That is what we call the action at a distance. Okay? But special theory of relativity restricts that. Every body interacts with another body at certain speed, at certain velocity, okay? Or the interaction between any two bodies occurs at certain speed. There is a finite limit to that speed, and that's the highest limit of that speed is velocity of light. Okay? Let's take this. Okay, so this is a universal thing. In all inertial frames of references, this velocity is constant. Okay? Have you heard about the gravitational lensing? Okay, let me tell you this way. Suppose if you are a particle is moving along a straight line, okay? So we can think it's okay. If it moves along a straight line, we can think the motion is rectilinear. Okay, let's assume the velocity is constant. Okay, it will go forever if there is no friction, is it? Clear? Now if the particle deviates, what you can say? Suppose if a particle goes along the straight line, but suddenly it deviates its path, what you can say? Velocity change, is it? Is that true? So that means, okay, you can think speed can be the constant throughout its journey, but it is actually the direction which it is changing. Okay? So much, same thing is happening with the velocity of light. When we are passing through the high gravitational fields, is it? You actually observe different kinds of stars through what we call the gravitational lensing. Or let's say if you are having a heavy mass where there is gravity is very large, is it? This actually this bends. Light actually bends there, is it? So when you are having a bending of light, what you can think? It's a deflection from what you can think. Velocity is changing actually. It depends on the coordinate there, how intense the gravitational field is it? So that's a different kind of story. I just want to mention it. But since we are all here dealing with the inertial frames of references, for all inertial purpose, this is a constant. This is a fundamental constant. And in nature, it's actually the fundamental constant. This is the highest speed what we can achieve. We don't have the speeds beyond c. Okay? So there isn't any kind of object in nature which move actually beyond c. So some people call there are tachyons existing in nature. Okay? I don't know. Okay? Which are moving far beyond the velocity of light, but it's actually the fundamental thing. It's experimental. It's actually an experimental fact as well. Okay? People have verified it experimentally. Okay. So now let's consider, now since we are in the four-dimensional space-time, let's consider two frames. Okay? So let's consider a frame of reference. Okay, so we are having some time here. Okay, let's call this as a K frame. Okay. So let's think of an event in this very frame. Okay, let's take this very point where an event is happening. Okay, let's assign the coordinates to this very point: x1, y1, z1, t1. Okay, it's in the frame K. Okay, so think of this event as sending a signal from this very point. Let's say you are having a point A to some point B in the same frame. Okay, and you assign some other coordinate. So this is another event. So this is an event where you send a signal from point A to point B. This is also an event where you receive the same signal, is it? Okay. Now if you send a signal, the signal travels at the speed of light, is it? So how much distance it covers? Now tell me. Okay. Tell me. So the signal covers a distance of c into t2 minus t1, is it? So this is the distance covered. Teacher? Clear? Okay, now tell me what is the, okay, forget about a timed coordinate here. What is the distance between these 2 points? Yes. Yes, x2 minus x1 whole square plus y2. Okay. So I can say then, so square of this very quantity, that's actually equal to x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. So this is actually the distance traveled by the signal between the 2 points, and that distance is spatially equal to this. This is a square distance. Clear? So now we can rearrange it. So or I can write it as c square t2 minus t1 square minus x2 minus x1 square y2 minus y1 square minus z2 minus z. You can do the other way as well. Okay, you can put actually a minus sign here and plus signs here. So it's equally valid. There is no problem. Okay, but I will be using a convention defining it in this way. So there, okay, now here you should note, you will be having two types of conventions arising here. Either you put a minus here and plus, 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 is it? So just rearranging the terms, is it? Or another convention is this thing. You put a plus sign here and negative sign. I will be using this kind of convention, okay? Both are correct. Okay, so this is actually in K frame. Now the same events we can observe from where? In K prime system. Okay. So you will be having a K prime system. You observe the same kind of events. Let's say at some point A prime, B prime. So you call it as x1 prime, y1 prime, z1 prime, t1 prime. Okay, and x2 prime, y2 prime, z2 prime, t2 prime. Okay. So we can have the same kind of relation here in K prime frame. Okay, c square t2 prime minus t1. Okay, because c is constant, is it?
Yes, sir.
So it's an invariant quantity. Okay, minus x2 prime minus x1 prime square minus y2 prime minus y1 prime square minus z2 prime minus z1 prime square, that's equal to 0. Let's call this as first and call this as second. Okay, let's define a quantity called as interval, or the length of the interval. Samajh? Interval means the distance between 2 points. Samajh? 2 events in a given frame of reference. Okay, we define it, let's say S12 square, like this thing. So we define it in this way: c square t2 minus t1 square minus x2 minus x1 square minus y2 minus y1 square minus z2 minus z1 square. So this is in K frame, or S12 prime square. So 1 and 2 means, so 1 is the first event, 2 means the second event. Okay, so you can think this is the length between 2 events. Samajh?
Yes, sir.
Got it? So this is just a definition. Now look here, there is a, okay, let me write first this very quantity as well, then I can tell you square minus x1 prime square minus y2 prime. Okay, now if these events are infinitesimally close to each other, okay, so if they are infinitesimally close to each other, that means this x, okay, t2 minus t1, you can say it is a dt. So much.
Yes, sir.
So in that case, I can write for infinitesimally close events, we can write it as like this thing: ds square. Okay, I will drop now 1 to a ds square as c square dt square minus dx square minus dy square minus dz square, or ds prime square as c square dt prime square minus dx prime square. Let's call this as equation. Okay, so now what this ds gives me? It simply gives me the length between the 2 points, is it? Now look here, if you are in the simple geometry, when you do, how you define the length? Simply the sum of the squares, is it? Length square is equal to the sum of squares of the coordinate differences, is it? But it is not the sum of the squares, is it? So in usual Euclidean geometry, what you normally know, okay, so there you write the distance between 2 points, or the square of the distance between 2 points as sum of squares of the coordinate differences of the 2 points, is it? But it's not the sum of squares, is it? So there is a subtraction here. Or you can think, if we use the convention where you can put minus sign here, plus sign here, plus sign here, plus sign here, is it? You can use that kind of convention as well. So that means you don't have actually the same sign throughout, okay? So that's why we don't call it as a Euclidean, we call it as a pseudo-Euclidean. Or in other words, we call it as a Minkowski geometry. So this defines a new kind of geometry, what we call what? Minkowski geometry. So it's a simple Euclidean geometry, but where the length or the distance between 2 points is not given by the sum of the squares, but there is actually the sign change between different terms. That's why it is different than the usual Euclidean geometry. Okay? Clear? Okay, now the point is here. Look at this very thing. Okay. So we are having these two equations. So this is, okay, let's assume, so what it gives me? So tell me what this gives me. It gives me the distance between the 2 points, is it? Or in other words, that distance we call it the interval. So much on? When I am saying, okay, so from this very equation, interval, if interval in one coordinate system is 0, then it is the same thing in other thing, is it? In the other coordinate system. So this difference is again what? 0. So it means if this ds vanishes in one frame of reference, so that means in another frame of reference this ds also vanishes. So samajh aaya? You got my point? So it means when we move from one coordinate system to the another coordinate system, this ds remains invariant. Okay? Oh, you got it? So invariant in a sense. So if you keep one, okay, this ds to be 0, so in another frame of reference it will again be 0. So this ds is actually an absolute quantity. Okay, we'll try to figure it out. Okay, how? Okay, now look here at this very ds. Actually, this very relation gives me the second postulate of the theory of relativity. What is the second postulate? Velocity is constant, is it? So now if you see in both the terms, actually velocity is same. We have not changed velocity. Is that true? Okay, we'll prove it in a moment. Okay? So now let's do that. Okay, before doing that, okay, so the first point is observation from first and second. If the interval is 0 in one frame of reference, it is 0 in where? Another frame of reference. So this is the first observation. Second observation is that, so ds square, it's order of this dt square. Okay, so this quadratic order, is it? ds prime is also of what? So the order of magnitude of both ds and ds prime, they are same, is it? In other words, okay, from this observation and that observation, we can say this ds and ds prime are proportional to each other. So if I want them to be, okay, if I keep, let's say, 0 in one frame of reference, another is also 0, is it? So it implies they should be proportional, is it? Okay? So now let's write it.